Hello, now we're going to do part 2 of chapter 10, talking about the attributes and functions of lipids in foods, and then we'll go into the diet. So, so first we're going to get into physical characteristics of lipids, and there is a list of physical characteristics in several subsections in the book. The first is the melting and solidification points. So the idea that I want to make sure that we understand here is that a mixture of a certain set of fatty acids, which is what an oil or a fat is it's a mixture of fatty acids, and that mixture has a certain melting point. But if we have another mixture of fatty acids that have just a different combination, it might even have the same fatty acids, but in different proportions, it's going to have a different melting point. And so there is not, so let me back up. So each fatty acid brings its own melting point to the table, and that kind of gives you an overall average melting point. But they're going to melt at different rates or solidify at different rates. And so there's not one melting point of in an oil or of an oil um, description. Okay, so like for example, olive oil. Well, depending on where you got the olives, what variety of olives, all kinds of different things, it's going to have it's a natural substance. It's going to have natural variation and may have different proportions of the fatty acids from one batch to another. Okay, sorry, had to deal with the cat. So there is variation. So even some of these numbers I give you, they are not set in stone. One sunflower oil is going to have a different melting point than another sunflower oil from another company sourced from a different area. Lard and tallow, especially, where it depends on where on the animal you got it, um, where the animal was from, what the animal's diet was, all kinds of things. But so these are just kind of generalizations. Now, when we're talking, so let's go into the definitions here. So melting point, temperature at which the substance changes from a solid to a liquid. Okay, we've learned melting point before and phase changes. That makes sense. Now the difference here with the oils is that we have melting point and solidification points, and they are completely different temperatures. Okay, now I've modified the definition of the solidification point from what is in the book, and it oops, and my modification is pretty important, so make sure you understand this. The solidification point is the temperature at which the majority of lipids in the mixture are in the solid state. Okay, and so the mixture is now behaving like a solid. The reason I say this is because we're going to have some fatty acids that are, even in a much more saturated fat like tallow, there are going to be some fatty acids like arachidonic acid that melt at extremely low temperatures. And but the tallow is going to be solid at temperatures well above that because arachidonic acid is such a small proportion of that mixture of fatty acids. Okay, and so it's technically majority of it. And technically we could say that for melting point too. It's because the majority of lipids are in a liquid state, the whole overall substance changes from a solid to a liquid. Okay, and we see that with these temperatures here. The solidification point is much different than the melting point, okay? So sunflower oil solidification point is -30 degrees Celsius. The melting point is 13 degrees higher than that at -17 degrees Celsius. And the temperature in between is going to be a mixture. We have some of the fatty acids that are solid and some that are a liquid, and there is a true transition. This is different than phase changes where the melting point and solidification point, yes, there is a difference in energy that's in that substance, but the temperature stays the same, right? The melting point and solidification point are both 0 degrees when we're talking about water, for example. Okay. So important distinction to understand there. So the next physical characteristic is that lipids are nonpolar. So water molecules we know are polar. We've talked about this before. And what is polarity? The sharing of electrons is unbalanced. And so each end of the water molecule has a partial charge. In triglycerides and some other lipids, not all of the lipids, the electrons are equally shared. And so there is no partial charge anywhere. And this is going to make the molecules nonpolar. All right. And so they are not going to want to intermix with the polar molecules, and so we get this separation. Now, why do the fats and oils float? Why are they always going to be at the top in a water-oil mixture? Well, this is why. The structure of the fatty acids allows them to be packed, or doesn't allow them to be packed, I should say, as densely as water. Look at all this space in between here. And how are we going to get more fatty acids jammed up in here and packed nicely, like we've seen diagrams of water packed real nicely, you know, structure-wise, all very close together. The fatty acids just physically cannot do that. Even if we have a fatty acid that's all saturated and doesn't have bends, it's still a bulky molecule. And so it just cannot be packed as densely as the water molecules. And so that is why fat and oils will pretty much always float on top of water. So the other thing to note about them being nonpolar is so some lipids, like phospholipids, I've kind of briefly mentioned last week that they are can be emulsifiers. They have a polar end and a nonpolar end. And so emulsifiers, such as phospholipids, there are other ones out there, have a polar end that's able to mix with the water, and a nonpolar end that can mix with the oil. And these allow the oil to be suspended in the water, and this emulsifier is going to be bound to the oil, so it's going to kind of get it into the water too. So it allows the oil to be suspended in the water, or vice versa. If you have more oil than water, the emulsifier may allow the water to be suspended in the oil without separating. Next physical characteristic, the third one, is the tendency to deteriorate. And with this, we're talking about lipid oxidation. In the book, it calls it autooxidation. You can use the more simple term lipid oxidation. And it's called autooxidation because once this process starts, it is very self-perpetuating. It has this cycle. So what happens in lipid oxidation, kind of like briefly going into the chemistry of it and why it is cyclical, like this, or self-perpetuating, I should say. So you have these hydrogens that are on the lipid molecule, and specifically if they are the hydrogens that are on the carbon that is bound to a carbon that has a double bond. So not the carbon with the double bond, but the carbon next to it. It has two hydrogens on it. And these hydrogens are very susceptible to just getting removed. Um, and it can be caused by temperature. It can be caused by metal ions that just want to steal the hydrogen. It can be caused by light. So just the light can say boing and make the hydrogen jump off. Okay. When this hydrogen leaves the molecule, you now have a electron on the carbon that isn't paired up anymore. It was paired with the hydrogen. The hydrogen had one electron with it, and the carbon was happy. Well, now the hydrogen's gone, and so you have this electron that's from the carbon that is not paired up. And this is called a free radical, when you have just this spare electron hanging out, and it's unstable. So this free radical, then we get oxygen in the equation, so O2, and O2 will bind to the free radical, but there's still, it doesn't really fix the problem. There is still a free radical, but now it's on the oxygen end. And this is called a peroxide, when you have a double oxygen bound to a carbon here. Okay, and then this peroxide, so it's it will continue on and go back to having, actually, there's still a free radical, and you just get this self-perpetuating cycle of more free radicals being created, because this will now steal a hydrogen, and because hydrogen will go on nicely here, it will steal that hydrogen, you create another free radical, and it's over and over and over again. Okay. And so here I'm showing you, it's always this carbon that is bound to a carbon with a double bond that is susceptible to this. Okay, so this causes rancidity. I have completely changed the definition on this on you because the book definition is awful. It does not describe what rancidity is at all. So this is the definition you're using for rancidity. It is food spoilage caused by oxidation or hydrolysis, and we'll get to hydrolysis in a couple slides, of fat marked by unpleasant odor or flavor. Okay. So what's important here is that the more double bonds there are, the more opportunities for lipid oxidation to occur. There's going to be more of these carbons that are connected to the carbons with double bonds that are susceptible to this lipid oxidation. So overall, the more double bonds a lipid has, the more susceptible to oxidation and the less stable the oil is. Okay, the more likely it is to deteriorate. So how do we prevent this? Okay, number one, reduce exposure to oxygen. That stops it in its tracks right here. Okay, so we get here, doesn't continue any further. Number two, reducing exposure to light. This is why you'll see a lot of your more polyunsaturated oils, they are stored in dark containers, like olive oil. Olive oil is pretty susceptible to lipid oxidation, even though it is mostly monounsaturated fat, or a good amount of monounsaturated fat, but it's pretty susceptible to lipid oxidation. And so that's why you'll see olive oil in dark containers. We'll see the same thing for avocado oil, for grapeseed oil. And so those dark containers have a purpose. It's not just to hide from you what color the oil is. It's not that at all. It's to help protect that oil from lipid oxidation and keep it from deteriorating. Also reducing exposure to free metal ions. So you wouldn't want to be mixing things with oils in an iron bowl, for example. Okay, it's kind of weird. Or a copper bowl. That might be more realistic. If you're doing something that has a lot of polyunsaturated fat in it, because that does expose it to metal ions, which can cause some deterioration. Now, is it going to cause rancidity just like that? No, but you would definitely wouldn't want to store it in a copper bowl. Okay. Also keeping the temperature low. As we know with all reactions, the higher the temperature is, the faster the reaction takes place. And the final thing is to add antioxidants. So what are antioxidants exactly? So antioxidants are molecules that will preferably react with oxidation products by donating an electron. So what these do, they stop the lipid oxidation self-perpetuating cycle in its tracks. So you have a free radical here or here, okay? And so this molecule is unstable. What the antioxidant does is instead of this free radical being able to steal an electron from a stable molecule, so it's like steal this hydrogen here from a stable molecule, the antioxidant says, oh, here you go, you can have this one, okay? And then now this isn't a free radical anymore. It becomes a stable molecule. Okay. Antioxidants. So you're saying, well, what happens now? This one doesn't have the right number of electrons, although this guy does. He actually has a completely extra electron, but some of them don't. Some of them have 4, and they do become free radicals themselves. But they are these particular molecules, they're antioxidants because they are more stable, even if they've lost that electron, than the lipid free radicals, and so they're not as reactive trying to steal electrons. So even though there might be technically free radicals also, they aren't harmful. Okay, so the first way that lipids can deteriorate is lipid oxidation. The second way is hydrolysis. So hydrolysis is completely different than lipid oxidation. The paragraph in the book that talks about hydrolysis is in the middle between a paragraph talking about oxidation and then the ones talking about antioxidants. And so it makes it sound like it's all the same thing, and it should not be. It's confusing. It also mentions oxidation at the end of that paragraph when it's talking about hydrolysis, and that's actually a typo. Where it says oxidize in that paragraph, it should say hydrolyze. Okay, so completely different process than lipid oxidation. And we've already learned about hydrolysis with carbohydrates. Okay, so this should be fairly easy. This is the same reaction except in lipids, just like with carbohydrates. We use water to break apart the lipid. Okay, so with carbohydrates, we use water to break apart the carbohydrate, right? Hydrolysis and lipids use water to break apart the lipid. Now, just like with carbohydrates, generally more than water, more than just water is needed in general. Something needs to catalyze the reaction to kind of get it to where it can do it with the energy it has. So the book makes it sound like only water is needed. Ignore that. We usually need something else to happen. Okay, usually an enzyme, heat, acids, bases, etc. Okay, so water is added, lipid is broken apart, usually requires an enzyme, a strong acid or a base, or heat for it to occur. It doesn't just occur willy-nilly. And you'll see why in a second. Now, also something different from the book. I just don't like this paragraph in the book. Okay, so the book refers to rancidity with hydrolysis, and this is actually correct, but it's a different kind of rancidity than with lipid oxidation. And in my rancidity definition, we included hydrolysis, okay? So this particular rancidity, we refer it more specifically to as hydrolytic rancidity, okay? Rancidity due to hydrolysis, hydrolytic, okay? Now, short chain fatty acids, so the ones that have fewer carbons, are easier to hydrolyze. And I think this is where the book said oxidize and hydrolyze, okay? So these can be found in high amounts in milk, okay? It's one of the main places that we find these short chain fatty acids is in milk, okay? So now there's a lot of water in milk, right? And so if you kind of follow the book and it's just only water's needed, well, why isn't milk always sour and gross? Well, because it just doesn't freely hydrolyze all the time. It needs something else. Now, spoilage bacteria have lipases, which is an enzyme that helps with hydrolysis of lipids. And so they attack the fatty acids, releasing them from the triglyceride. So here we have a triglyceride, the lipase comes in, and that first fatty acid is now gone. And we've added water. Then another molecule of water comes in with another lipase reaction, and this third fatty acid is gone. And so at this point, it's now a monoglyceride. Okay, and we've lost 2 fatty acids. And we have these 2 free fatty acids floating around. Well, free fatty acids don't taste good. And especially these short chain fatty acids, they are gross. And these fatty acids, like from milk especially, is how we get the smell and flavor of rancid milk. Okay, so you can even think about buttermilk. All right, buttermilk has some of these fatty acids that have been released, but really more specifically, like, I mean, think about curdled nasty milk that was in your fridge that you were gone on vacation and came back to it and the fridge had died. Like, and you smell it and it's that gross. And that is because of hydrolysis occurring to those fatty acids. Now, sometimes hydrolysis is actually desired. And the one example that I can think of is soap making. So in the process of making soap, we have a lipid. We add sodium hydroxide and heat. So we have a strong acid, or sorry, strong base and heat. And that causes the fatty acids to come off. And then you have the free fatty acids, and this is soap. So, and they're also bound to sodium. So, okay. So now let's switch over into the functions of lipids in food preparation. So previously we're talking about physical characteristics of lipids. Now we're talking about functions in food preparation. Okay, a lot of you on the last exam, you were giving me functions of carbohydrates, but when the question asked for how they relate to food preparation. So if you give me a function about diet when I'm asking about food preparation, that's not going to work. So make sure you're paying attention to what the functions I'm asking for are. Okay. So the first function is to transfer heat. And so we know that lipids can get much hotter than water. As a food is frying in lipid, the water boils off the food and that food is able to brown. Okay. Now there is no boiling point of lipids. And that is just because the lipids will degrade before they get to a boiling point. Okay. So heat will cause degradation of the fatty acids before they can ever get to a point where they're boiling. So we never even talk about a boiling point of lipids. Now, if you see fat and it looks like, or oil and it looks like it's boiling, well, that's because there's water in it. And the water is causing that action. Okay. If you notice, like, it always looks nice and still until you added that food. Well, the more moisture is in that food, the crazier the oil gets. And that's because it's the water boiling off, not the fat itself. Okay. Now, however, as they are degrading based on the temperature, we do get smoking that happens. And so the smoke point is the temperature at which fatty acids begin to break apart and produce smoke. And it changes depending on the lipid. Some oils are much better than others. being subjected to high heat. So avocado oil is a great lipid as far as being able to handle high heat. Refined avocado oil has a smoke point of 500 degrees, which is very high. Okay, versus other oils like flaxseed or almond oil, you don't put that under any heat at all. You just toss it in your salad because any heat at all and it will smoke and it's not going to taste good. All right, those breakdown products don't taste any better when they've smoked versus the hydrolytic rancidity. Okay. Um, Now, when I say refined, that means that it's undergone further procedures to purify the oil. That could include chemical treatments in which the chemicals are later removed, so the chemicals aren't in the oil that you're consuming, steaming, pressing, additional filtering, etc. So and the more that they refine it, generally the higher that smoke point is, so the higher the temperature that oil can be cooked at. So like avocado oil, if it's refined, has a smoke point around 500 degrees. And but if it's unrefined, it's more like 350 to 400. Okay. And so yeah, these breakdown products do not taste good. We don't want to get oils to their smoke point. If this oil is smoking and breaking down, it is also likely producing free radicals and going rancid at a rapid rate also. So all just bad news. Now, if you continue to cook this oil well past the smoke point, you can reach the flash point. And the flash point is actually pretty consistent across all the oils, and it's about 600 degrees Fahrenheit. So you have to really get that oil hot to get the flash point. But if you drop oil onto a fire, it's immediately hit that 600 degrees Fahrenheit and will flash and have a grease fire. Okay, continuing with transferring heat. So frying foods, you have to make sure that you are frying foods at a high temperature, but not too high. And so if you are frying foods at a temperature under 350 degrees Fahrenheit, it's not going to be hot enough to really flash fry that food. And so the oil will actually soak into the food and you end up with greasy, soggy food that doesn't have a brown exterior. It doesn't do a good job of boiling off that water. And so you get fries that look like that, right? If you have your temperature of your oil over 400 degrees Fahrenheit, then that oil is going to burn the food very quickly. But it's going to be burning the exterior and the heat's not penetrating the interior fast enough before the exterior is completely burnt and you get stuff that looks like that. Okay, so other frying tips, using a deep fryer, even a home one, will usually have temperature settings, right? It's not just low, high, medium, or a dial that you can't tell what the temperature is. But an actual temperature setting, and it will the thermostat will turn on and off the fryer to keep it at the correct temperature. Also, as you're frying, if the more evenly sized you can keep the food, the better, so you don't have some overcooked and some undercooked pieces. If you can, it helps a lot to have a dry exterior and not be putting something super wet into the oil, because that causes the oil to quickly boil off that water and crazy splattering occurring. So great example that, we just got out of Thanksgiving and turkey frying season. And if you've never seen a video of somebody practically burning their house down with a turkey fryer, watch that sometime. And that a lot of times there's two things that people do, well, several things that people do wrong. One, they put them too close to their house. Two, they don't test to see what the level of the oil is after the bird is going to be put in, and so the oil overflows. Three, they don't turn off their burner while they're putting the bird in. But the fourth one that has more to do with what we're talking about is they don't make sure that they've dried the outside of the turkey as much as they can before they drop it in. If they're putting a very wet turkey in there, it's much more likely that that oil is going to be going all over the place and then jumping out of their fryer and hitting their burner that shouldn't be still on while they're lowering it in and causing a crazy fire. You can turn the burner on after you get the turkey in and the oil has settled down. Okay. And finally, don't add too much of to the fryer at once. So if, based on the volume of food that you're adding, if you add too much to the fryer at once, you're going to lower the fryer temperature and you might get it, down to this temperature, which is you're going to cause that problem if you've added too much food. With breaded foods, kind of going back to what we learned with our complex carbohydrates chapter, is allow that breading to sit and the binding to occur for 20 to 30 minutes before frying. And finally, salt your foods after you fry them, not before. And that is for two reasons. Salt draws water to the surface, and that causes increased splattering of oil. So you get even more crazy oil action. And then two, salt will reduce the smoke point of oil and damage the oil quality faster. And so you end up with oil that is not tasty if you are salting before you fry. Okay, so second function of lipids in food preparation is tenderizing. And so we're going to be talking mostly about baking here. So if we add fat, it prevents long gluten strands from forming. It just kind of, goes in between there, and there's a barrier, and the gluten strand can't be as long. Gluten is the toughness of bread. It's like the biggest structure component of bread. And so having fat in there just makes the bread less chewy and tough. Also, the more fat you have will be a flakier product. And so because it prevents long gluten strands from forming, that's where we get the name shortening, because like the vegetable oil shortening, it actually does shorten the gluten strands. Okay. So too much fat, or fat that is blended in too much. So here's an example of fat blending. So they've added butter and shortening here, and you blend it in this type of product, just so you get like pea-sized pieces of the fat in there that's all coated with the flour mixture. But if we blend it too much, or we add too much fat, that it will completely prevent the gluten strand development, which can have the opposite effect. You can have a greasy, dense bread that can't hold its structure, because gluten is structure, and therefore it can't even trap air. So here is example of little experiment where they added between 3 and 20% fat, and you can see that this 20% fat bread was not able to get the same rise as the 3, 5, or 10% fat. Okay, and the 3 was less rise than the 5 or 10 because the structure was too much, and it prevented the rise from occurring with less fat. Okay, so with less fat, without fat at all, shorter, just denser bread, and with fat, it's able to get the rise. So that was, hold on a second, let me make sure my desktop audio is on. Okay. So that was about like baking and rising. Here I'm gonna have you just watch this video about puff pastry, I think. Can I start it? Okay.
There are two main methods to get the hundreds of layers you want on your puff pastry. Full puff pastry is made by flattening a block of butter and locking it in between layers of dough. Roll and fold the dough several times to get thin, even sheets of butter that separate each layer. After just 2 folds, the layers of butter and dough are still thick and easily separated. Once you get to 4 or even up to 6 folds, the dough has hundreds of crispy layers. For rough puff pastry, the butter is first cut into cubes and incorporated into the dough before rolling and folding the same as before. You still need to chill the dough after each pair of folds to keep the butter cold and prevent it from melting into the dough, but there's slightly less to worry about compared to the process for full puff. You're still creating thin layers of butter in the dough, but they won't be as distinct as the ones in full puff. If you're intimidated by full puff pastry though, I recommend trying rough puff, and with 4 to 6 folds, you can get an amazing flaky pastry.
Okay, so that was puff pastry and how we use fat there to create these layers that lead to a very tender pastry. Now notice how the person in the video says that the butter must stay cold. In both the puff pastry technique and the cutting in technique, the goal is for the fat to separate the dough, but not to blend into it. So for doughs then, we want to use fats that are going to be solid at room temperature so that they don't melt into these types of doughs before we are cooking it. So that means butter, lard, or shortenings. Now there are situations where we're going to use oils, and we'll talk about that. Okay. Okay, so when do we use what type of fat? So doughs for flaky breads, we're going to use solid to have that best flake. So like, here's a little example. This is a puff pastry that is just twisted and made with oils versus made with butter, right? Big difference there. Okay, this is biscuits where you would like cut in your butter and sorry. And most people say butter, but this there's a video, I think I put it in our playlist for this week that you're welcome to watch. And this person tried vegetable oil and it turned out really good biscuit. So now this isn't a super flaky biscuit, I guess. But oils can work in some situations too, even though it's like a more bread type product. Okay. Now for yeast breads, it's kind of your preference. There is another video that I posted in the playlist. This person used, oh gosh, I think olive oil. This is rapeseed or canola oil. That's 2 names for the same thing. Butter, and this here is actually bacon, and they rendered out the fat in the bacon so that it was lard. They used homemade lard for it. And they all had different textures and flavors. The butter and the lard have the best flavor, but is really kind of your preference kind of thing for what you are desiring in your bread for as far as texture and flavor. For quick mix type batters, such as cakes, waffles, etc., oils work fine because they are, there's less gluten structure that is required, and so oils tend to make cakes taste more moist as far as mouthfeel. Oils will actually allow a better rise than butter in a lot of cases. And it all depends on the bread and what the recipe is, what modifications have been done to the recipe, etc. Cookies, it's your preference. Using softened butter helps with shaping, both because air pockets can be whipped into it and trapped, and we'll talk about that in a little bit. Oil is going to be more compact. So if you use an oil, the dough will be softer. It's going to spread out more on the pan just because the mixture is going to be more liquid. And it's going to often tend to have crispy fried edges. Some people like this, so it's really up to you. Flavor is something to consider. So for example, in this experiment here, so they use shortening. Shortening is very bland. It doesn't have really much flavor at all. It also has a higher melting point than butter, so it will have less spread in the cookie. And the other thing to consider, and if you are substituting oils for butter, butter has water in it. Butter has between 10 and 20% water as part of it. And so if you're completely doing a full substitution of another fat, you actually have less moisture in your mixture. So that's something to consider. The cookies here, made with, anything besides butter are going to be drier in general, but although the vegetable oil cookie will feel more moist because oil has a lower melting point and you feel it in your mouth, and your mouth detects it as moisture. So you can make tweaks to these to make them better. This experiment was just like 1-to-1 replacement of all of these. By the way, tahini is basically ground up sesame seeds made into like a butter, and they said it was really gross in this cookie. So okay, so next function of lipids in food preparation, the third one is aerate, which aeration is the addition of air into a batter. This is also called mechanical leavening. So we've talked about leavening, chemical leavening, when we're adding baking soda and baking powder. This is mechanical leavening. We've done something to physically add air bubbles into our mixture. Okay, and the key thing here is that it's only saturated fats that have this aeration function. By mixing the saturated fats at a high level, you can allow air pockets to form. And so this is what we're doing when in a recipe it asks you to cream the butter and sugar before mixing it in to something else. And it'll tell you to cream that butter and sugar until it is light and fluffy. And this fluffiness indicates that the air has been incorporated. So here's some pictures here. So it's under creamed. Like you actually see a color difference, right? Where it does become lighter in color as you cream it and incorporate that air. But you can over cream it and not have as much air, and that kind of cause a problem. So under creaming, not enough air will be incorporated, and so you won't get that nice rise. And over creaming, you could have too much air in there, and it won't have as good of a structure of those air pockets, and they'll easily collapse, and the cake can end up being gummy and dense. Okay, so here is some pictures. So under creamed is clearly flatter than our creamed one. And then we've got perfectly creamed, and then the over creamed one. It ends up being darker because you've extracted, like more of the sugar ends up on the exterior, and so that as that bakes, it browns more. And that sugar is what leads to it being gummy too, because like wet sugar is sticky, right? So that's what happens if you over cream your butter and sugar. Okay, so continuing with aerate, we also see this in whipped versions of butter or margarine. So you can buy just regular butter that has been whipped and it's in a tub. The book says sticks, talks about sticks. Whipped butter isn't really sold in sticks, at least not now. I don't know if it used to be. Now, you are paying for them to whip it, so you could whip this yourself. It's just blending it, blend it with a hand mixer or in your KitchenAid mixer or whatever. But you do pay for this. So like this here is $4.32, but we can buy twice as much actual butter in a stick for $5.92. So if we're talking about like same amount versus same amount, it'd be like $4.32, or the same amount in stick butter for $2.96. Okay, so you're paying a premium of $1.50 almost to buy it pre-whipped. Okay. Um, you can also find some vegetable oil spreads, margarine, that say that they're whipped. Usually they're not, because they don't really need to be. Vegetable oil spreads, they're easily able to make them the consistency that they want by changing the ratios of the fatty acids and having more polyunsaturated fats or monounsaturated fats in the mixture. The other thing that vegetable oil spreads have is water. And so that makes it, when they're mixing all that in, makes it more easy to spread. So like this particular one has 42% water. It's 58% vegetable oil, 42% water. Some of them have even more than that. There's a Country Crock version of a vegetable oil spread that has 62% water. So you're only buying 32%, or sorry, 38% actual oils by weight of that spread. Now sometimes butters are spreads, but they're not whipped. And what's happened there is they've usually incorporated it, oils into it. So this Land O'Lakes spreadable butter, they have olive oil in it to make it a little bit softer. Now olive oil is actually a solid at refrigeration temperatures too, but it's a little bit softer than butter. Okay. Okay. So the fourth function of lipids in food preparation, we're getting into an obvious one, flavor. Okay, fat is flavor. Fat gives flavor. Adding fat to anything makes it taste better. So when you're cooking, choose oils or fats that have the flavor you desire. Oils with sometimes you don't want to add flavor. You just want to taste what you have. And so options that are good for that. Cottonseed, that's not really sold in stores. It's more of used in the food industry. But cottonseed oil has very little flavor. So often like your potato chips are fried in cottonseed oil because they don't, it doesn't add flavor to the chips. Vegetable shortening, I've already mentioned, has very little flavor. Soybean oil, or canola oil. Canola oil has some flavor, but it's on the lower end of the oils as far as how much flavor it will add to your food. Okay, I think we're on the fifth one. Lubricate. So lubrication of fats in our food make the food slippery and easier to chew. And this is one of several reasons that marbling in steaks makes the steak more tender. It's just easier to chew through that because there's all these fat pockets and it lubricates everything and your teeth slide through the steak more easily. Okay. The other thing about lubrication is that it gives you an enhanced moisture sensation without actually adding moisture. So like I like to think of so like these rolls, they look like they've been drenched in butter. Or like I have a ham and cheese slider recipe that is basically drenched in butter. But if I and so it's so moist and juicy, it's so good, right? But if I did the same thing with water and I like subbed out my butter for water, that drenched in water would not be nearly as appetizing, right? Not just from the flavor standpoint, but instead of it just feeling moist, it would actually be moist and we would have soggy, disgusting bread, right? So that is the benefit of fat and lubrication, is it adds that moisture sensation without actually adding water. Okay, and I think this might be the last one. The functions of last function of lipids in food preparation is serving as liquids in emulsions. Okay, so a better way to say this, and feel free to change how you say this function. Okay, so instead of saying serve as liquids and emulsions, you can say it's part of emulsions or it's one part of emulsions. Okay, that is a better way to describe this function. Okay, so what is an emulsion? We've actually kind of already gone over this. It's a mixture that contains a nonpolar lipid and water or a polar liquid. Okay. So we have the nonpolar lipid here and water or some other polar liquid. Okay, so in order for this to happen, because water and oil don't naturally form a mixture, is that we must have an emulsifier or an emulsifying agent. Two words for the same thing. And so in this diagram, the emulsifier is this little red thing with a stick, okay? Phospholipids, as we've already mentioned, are great emulsifiers. So some examples of emulsions. Mayonnaise is an emulsion. And so we've mixed oil and water there. And the emulsifier, all of the things in parentheses are going to be our emulsifiers in these emulsions, is the lecithin, which is a phospholipid, that is found in eggs. Okay, so in homemade mayonnaise, you add an egg and your oil and your water and blend it all together, and then it becomes a mixture because of that lecithin in the eggs. Now, in commercial mayonnaise, you typically don't find eggs in mayonnaise anymore. They get lecithin from another source, such as sunflower. Okay, salad dressings, they can have various different emulsifiers. Lecithin is one, polysorbate, xanthan gum are all act as emulsifiers in salad dressings. Milk is an emulsified product. All right, just milk that you get from the grocery store. And butter is also an emulsion. Now, both of these have milk proteins as their emulsifier. So milk is what we call an oil and water emulsion. Okay, so the main component is water, and then you have some oil, and it is dispersed in there. Now, so raw milk, or non-homogenized milk, right? That cream does float to the top, right? And so that isn't really an emulsion until it has been homogenized. So more what you find in the grocery store. So how homogenization works, because it's not adding any kind of emulsifier, it reduces the size of the fat particles in the cream to such an extent that they can be trapped by the milk proteins, effectively allowing it to be emulsified. So before homogenization occurs, those fat particles in the cream, they're too big to have this kind of encapsulation of the milk proteins around the oil, and then the water surround that. And so what homogenization does, reduces the size of those fat particles so that this can occur kind of quote unquote naturally with the natural milk proteins that are already there. Okay, now butter is an inversion of that emulsion. Okay, we take the cream out of the milk, and so we have mostly oil, mostly fat, but there is still some water component to it. And what we've basically done is the cream, like if you buy heavy whipping cream, it's liquid, right? And that is an oil and water emulsion. But then you churn it and you invert that emulsion. And so now those same milk proteins are surrounding the water and allowing the oil to go on the outside. Okay. And it becomes a water and oil emulsion. Yeah, and I just realized, like, I grabbed this online, and the spelling on this is all crazy. It should say emulsion and emulsion on both of these. Okay, so now completely changing gears and talking about lipids in the diet. Okay, so what are the functions of lipids in the body? So it tells you in the book that there are 7, and then it's like really not clear like exactly what 7 they're talking about, because there's 6 paragraphs following that. So there's some that are kind of mixed up. So here are my 7, okay? If we're going to number them. Okay, lipids are a concentrated source of energy. So we've talked about carbohydrates are 4 calories per gram. Lipids are 9 calories per gram. So there is more energy in a gram of lipids than there is in a gram of carbohydrates. And so it's a concentrated source of energy and a steady supply of energy to the body between meals. Okay, so stored by your body, and it's a steady supply of energy that your body always has between meals, when you haven't eaten enough, any of that. Lipids contribute to a feeling of fullness. So the more fat you have in your diet, the more full you feel. And that is because fats take longer to digest. So I've talked about my keto diet before. And one of the things that like you go on the message boards for this, and trying to get advice from people who've done it for a while, and one of the things that they'll say when somebody will ask, like, I don't know, how are you doing this? I am hungry all the time. And they will say, you're not eating enough fat. And so having enough fat keeps your hunger levels down with that diet. Number 3, adipose tissue acts as an insulator, regulating body temperature. So within your body, the exterior fat helps keep you warm. Fat surrounds the vital organs to protect them. Okay, so like around your organs, fat provides cushioning to protect them from just any kind of jostles that you get. Number 5, lipids are used to transport vitamins A, D, E, and K. These are the fat-soluble vitamins, which we'll learn about in a later chapter. But because they are fat-soluble, they need fat with them to transport them. Number 6, production of hormones, vitamins, and other secretions. We're going to get into this a little bit, but lipids, specifically cholesterol, is vital for production of your body's hormones. And number 7, essential fatty acids, so the lipids that are essential are needed for cell membranes, for immune function, inflammation regulation, and more. So essential, vital to your body. So let's get into those a little bit more. Okay. So essential fatty acids means fatty acids that cannot be produced by the human body. So we can take a lot of fatty acids and turn them into something else. We can make fatty acids ourselves, either converting one type of fatty acid to another. I don't know if we can do any. We have to be able to. But that's the biggest thing that we do is we take one fatty acid and convert it to another. But there are 2 that we absolutely cannot do that with. And those are linoleic acid, which is our 18 carbon fatty acid with 2 double bonds. And this is an omega-6 fatty acid. And linolenic acid, which is 18 carbons and 3 double bonds. And this is an omega-3 fatty acid. Okay. How I remember the difference between linoleic and linolenic is there's 1 extra letter, so it has 1 extra double bond. Okay. And can kind of help to say 3 double bonds and it's omega-3, but that's actually not why it's omega-3. Linolenic acid is sometimes called alpha linolenic acid. And so it's sometimes abbreviated ALA. You see that here. Now, most Americans have too much omega-6 fatty acid because it's in a lot of stuff. It's not hard to get omega-6 fatty acids in the American diet. It is found in high amounts in safflower, sunflower, corn oil, cottonseed oil, soybean oil, rice bran oil, peanut oil, canola oil. We consume lots of these, most Americans. And so there is no problem getting enough omega-6 fatty acid. And that is why we hear lots about needing omega-3 fatty acids, because we don't consume nearly enough of omega-3s on average. Now, foods that are high in linolenic acid, flax seeds, chia seeds, walnuts, canola, edamame, navy beans, cherimoya, avocados, roasted chicken, zucchini, and fish also has it too. Okay, now what is omega-6 and omega-3? What does that even mean? Okay, so let's talk about that naming system real quick. The number after the omega is based on where the first double bond is, counting from the opposite end of what we've been talking about before. So usually we have the glycerol over here, right? And then this is the fatty acid, okay? So these are free fatty acids. There's no glycerol on them, but the glycerol would be attached right here at this carboxyl group, okay? And so this is the end of the fatty acid. So with the omegas, we count from the end, okay? So this alpha linolenic acid. Now remember, each end or corner of this diagram is a carbon. So we have 1, 2, 3 carbons, and that third carbon is where the first double bond is, counting from the end. So this is omega-3. Okay. Eicosapentaenoic acid, 1, 2, 3. Docosahexaenoic acid, 1, 2, 3. Okay. Linoleic acid, 1, 2, 3, 4, 5, 6, right there. And arachidonic, 1, 2, 3, 4, 5, 6, right there. Okay. So that is how those are named. Now, our bodies are pretty good at converting linoleic acid to arachidonic acid. There's a reason all of these are on here, because they're all important fatty acids. So this one is not essential at all. As long as we have linoleic, we can produce arachidonic. We need arachidonic, but our bodies are able to produce it. But our bodies can produce eicosapentaenoic and docosahexaenoic acid from alpha-linolenic, but they're not very good at it. The conversion rate is really low. And so even though these two are not technically essential fatty acids, in actuality, in practice, we really do need to supplement with these. And by supplement, I mean like include these in our diet. So that is why there are often recommendations to consume foods that are rich in EPA and DHA, which are found primarily in fish oils. Okay, so omega-3 fatty acids in general, they support heart health. They lower the blood triglycerides, which are associated with heart disease. They slow the growth of plaque in the arteries, which we'll talk about in a little bit. They are important for brain function. They reduce joint inflammation, which is you'll get to when you get older. They prevent mental decline. So it's been shown that having a high diet that's high in omega-3 fatty acids, people who have a diet that is higher in omega-3 fatty acids have less propensity for Alzheimer's than those who don't consume enough. Okay, so certain fish are high in eicosapentaenoic and docosahexaenoic acid. In order of like how high they are, mackerel is the highest. It's one of the highest. Salmon, herring, and tuna. Now mackerel has double what tuna has. Okay, so it is quite a bit higher than the lowest on this list. and it has quadruple that if you're using eating light canned tuna. So like this is bluefin here. So it has albacore has a little bit less, and light canned has even less than that. It can also be found, omega-3s can also be found in those other foods that I listed for linolenic acid, so flaxseed, walnuts, edamame. Okay, now cholesterol. So our body makes cholesterol from lipids, and it is synthesized in the liver. So it's made in the liver. And cholesterol is vital for producing our body's hormones. So, you hear about cholesterol as a bad thing, but it is absolutely 100% necessary for our bodies. And so up to 40% of all our cell membranes are actually composed of cholesterol. And it does this weird thing where it adds stability, so it adds structure and elasticity. So it adds the structure, but also allows the cells to, I guess, bend without breaking, kind of thing. Now, we've heard a lot more about cholesterol as it relates to heart disease, so let's talk about that. So the first thing that we need to know about is lipoproteins. And so lipoproteins are clusters of lipid and protein molecules. So it's like a combination of a lipid and a protein made into one molecule, okay? And then there are clusters of them that are used to transport cholesterol in the blood. Notice red, there's a change as to what it says in the book for this definition. Okay. So there are two main types of lipoproteins. There's low density lipoprotein, which is also known as bad cholesterol. Okay. And this lipoprotein carries cholesterol from the liver. Okay. So cholesterol is produced in the liver, and the lipoprotein carries it from the liver to other parts of the body. Now, this serves an actual important healthy function. At normal levels, its role is to get the cholesterol that the liver makes to the cell membranes that it needs to be a part of, or to the hormone processing centers. The problem is that it becomes bad if there's too much LDL. Okay, and so high levels of like low density lipoprotein can cause atherosclerosis. So its function is to transport and drop off. Well, sometimes if there's too much of it, it's dropping off in not great places, such as your arteries. Okay, and so this is what atherosclerosis is deposits of plaque on the arteries. And as you can see here, as this plaque is deposited, the artery becomes narrower, and eventually it can be so narrow that blood can't get through, and that is what leads to a heart attack or a stroke. So heart attacks are caused by oxygen from the blood not getting to the heart. Strokes are oxygen not getting to the brain. Okay. So the other type of lipoprotein is high density lipoprotein. And this is often called our good cholesterol, because what it does is it finds unneeded cholesterol and it carries it back to the liver. Okay, so its function isn't to drop cholesterol off, it's to pick it up. So high density lipoprotein is good and protects against heart disease. So how does the diet affect our cholesterol? For most people, dietary cholesterol has no major effect on blood cholesterol. And so don't be paying attention to how much cholesterol your nutrition label says that your food has. So in the 1970s, the nutritionists thought that high cholesterol in the diet contributed to our body's high cholesterol. Eggs are really high in cholesterol, and they were villainized. 50 years later, we still consume far less eggs than we did then. And that's actually a major shame, because eggs are an excellent source of many nutrients, including one called choline, and 90% of Americans are deficient in choline. And eggs don't really raise your cholesterol at all. So that's kind of a shame of the whole nutrition field. Now, saturated fats have been implicated for raising cholesterol since about 1980, when the first dietary guidelines for Americans were introduced, and they instructed Americans to avoid too much fat, too much saturated fat, and too much cholesterol. So they were still on the cholesterol thing then. And they recommended that saturated fat be less than 10% of calories. They've quietly backed off on the less than 10% of calories recommendation, and you don't see that on nutrition labels anymore. So there actually are some data that saturated fat may not be as bad as previously thought. Okay, now these graphs here kind of show you how each kind of fat changes cholesterol. So this first one here, our saturated fatty acids are orange, monounsaturated green, polyunsaturated blue, and trans fats are here. Okay, so the saturated fats in this study raised the LDL, the bad cholesterol, by a decent amount. The trans fats were worse, okay? And the unsaturated fats reduced the LDL slightly. Then with good cholesterol, the saturated fatty acids increased good cholesterol, HDL, the most, followed by the other three in that order, with the trans fats not reducing it at all. Now, what tends to actually be more important than the level of one or the other is what the ratio is. So this total to LDL, it means total LDL to HDL ratio, not total cholesterol. So the ratio here is that the saturated fats don't change the ratio. The monounsaturated and polyunsaturated lower that ratio, meaning that for every amount of HDL, there is less LDL. And then the trans fats increase that ratio. So the biggest takeaway on this is trans fats are bad for you. And we know that, and that's why it's been mostly taken out of the diet. Now, trans fats are in every animal product naturally, but it's in very low amounts, and they're a type of trans fat that does not affect your body the way the ones in this study do. Okay, so you don't have to worry about animal fats and the trans fat and that. So the key thing here, unsaturated fats do lower the HDL and lower the LDL to HDL ratio, which is a positive. Some more recent studies suggest that monounsaturated fat is better than polyunsaturated fat, not because it's necessarily better with cholesterol, the effects are about the same, but because polyunsaturated fats, especially the omega-6 polyunsaturated fats, they oxidize very easily, including in our bodies. So things oxidizing in your bodies, that leads to inflammation, which can also lead to cancer, and aging. So you really want to reduce that as much as you prevent that as much as possible. Okay, so be careful of low or no fat versions of food if you're trying to watch this stuff, because often those foods are high in sugar or salt, which can be bad all on its own. And finally, cholesterol free, if you see it anywhere, that is a marketing gimmick. All animal products are going to have cholesterol in them, and not all plant-based products are going to have no cholesterol in them. And so it's one of those things that it's just on there for marketing, because they've realized that people are ignorant of what some of the labels mean, and cholesterol free sounds good. Okay, so that is all we have today. I'm sorry this video was a little bit longer than normal, but it's good stuff with the fats. All right, y'all have a great week.